Okay, so in this problem, we're looking for the maximum positive moment that can be developed at D. There's D right there. So I want to find the maximum moment developed at D for this problem. And also, the loading is a concentrated live load. So that's a point load that's moving. We have a uniform live load, 300 pounds per foot. That's where we can position it on the beam where it creates the maximum, in this case, positive moment. And then there's a dead load, which will have to go across the whole structure. So the first step is to find the influence line for the moment at B. Now you remember with our Mueller-Breslau principle, we come in here and we'll assume a connector that does not have moment capacity. And then I will kind of conceptually apply positive moment. So point D, under that particular influence, is it going to go up, down, or not move? I think it's going to drift up. Of course, when it does that, you can see that hinge down at E. It would go like this. It would seesaw over C. And then the hinge at B would allow it to break back. So there's quickly we can get the quantitative shape of the moment at D as a function of the position of the moving load. And I'll sketch these critical points down. And then I'll redraw it so you can see it a little more clearly. So there's the point that goes up. It seesaws over this, comes down, and then the hinge allows it to come back. So there's the shape of the moment at D. There's a couple other things here to notice. The dimensions 5, 5, and 5, if for example, I found this value right here, right, then what would the value here be? It would be the same, right? Because these two triangles are similar, and you'll notice that the base here is 5, and the base here is 5. So if I find this value, then I know that value, and then of course I know the values everywhere else. Likewise, I could find the moment at this point, when the unit load is at this position, I can find that moment. And I think that's the one I want to do. I think that would be a little easier to do. So what that, in effect, looks like is this. So we have a pin connector at A roller at C. Oh, I left out my hinge at B. And a roller at E. So there's the geometry of the structure. And I'm looking for this value, so that's when the unit load is at that position, 15 feet, which is right above D, which would be right here. So again, A, B, C, that's D, and E, and we know all the dimensions. So I need to find the moment at D when the unit load is at D. How do I do that? Well, more than likely, we're going to want to cut the structure there at D and look at the internal moment at D, and you can work the left side or the right side. Which one do you want to do?
The right side.
The right side. So if I'm going to work the right side, I need to find my reaction at E. How can I do that? Well, you'll notice I've got two here at this reaction, one at C, one at E. So I cannot draw a free body diagram of the whole structure. But I can break it apart right here, and I'll do that. So let's look at it this way. So I'll start here. I'll try to draw it in as much detail as possible so you can see it. So there's AY, and there's AX. There's the pin reactions. And then I come over to B, and I'll have Vy, Vx. Of course, they're equal and opposite onto B, and then I'll have from B to C all the way out here to E. So I would then have my reaction at C, Cy, and my reaction at E, Ey. So I just broke it apart there. And where's my unit load? Right here at D. So if I look at this free body right here, what are all these reactions? They are 0. There's no forces. Right? No force, no reaction. So that means that Vy and Vx are 0. So they're not there. So when I look at this free body, how many unknowns do I have? 2. Cy and Ey. Which one do I want? Ey. So what do I want to do? Some moments at C. Now the distance from C to D is 5 feet, and it's an additional 10 feet out here. So I'm going to have the moment produced by my unit load about C, which is negative with my sign convention. So 1 times the moment arm of 5. And then Ey creates positive moment about C with the moment arm of 15. So what's Ey equal to? 1/3. Now I can go back and actually cut the free body there. There's Ey, which I've just found is 1/3. This is where I didn't draw it quite right, but you'll get the idea. There's 1. I have the internal moment at C. And this is 10 feet. What did I write? D. You're right, D. D.
So
I drew this free body right here.
why did you take moment at C?
That was to find the reaction Ey.
So why didn't you consider Ey?
By is 0. Plus we solved this over here. What's By? If I sum moments about A, what do I have? By. That's it. So By is 0. If there's no moment, if there's no applied moment and there's no applied forces, what are your reactions? 0. And if there's 0 here, they have to be 0 there. So what's the moment at D? Well, I'll sum moments at the cut. And I have the moment at D, which is negative. I have my reaction Ey, which I just found, which creates positive moment. That's 1/3. And what's the distance? 10. So it looks like the moment at D is 10/3. So that means that this value right here is 10/3. So what is this value right here? Similar triangles tells you it has to be negative 10/3. And we have our influence line. This will also have the units of feet. And I think that's a little bit better approach than having to write 1, 2, 3 equations. And really it uses skills that you already have. Once you establish that you want the unit load at this point, then if I gave you a problem like this on the first part of the exam 1, or in part 1 of the of the test and said, what's the internal moment at D? You should be very, very happy.
How do you know dy is 0?
There's no loads applied there.
But you don't know what happens.
There's no load, Mr. Sanchez. There's no moment. There's nothing. 0. Nothing's applied. So what's to react? If you don't like that, some moments at A, what do you get? You get by times 5. And it has to be equal to 0. So by is 0.
Yeah, what hangs over my head is the dead load.
That we haven't got there yet. We're just drawing the influence line right now, right? And the influence line is based upon what? A unit load moving anywhere it wants on the beam. That's what this diagram says. And we've chosen to find the value when the unit load is right there. So that's how I got the position of the unit load at this point. If you wanted to solve for this value, then we'd have to move the unit load to B. And I would have to find the moment at D as the unit load was at B. I just thought this was an easier approach. So now that you have the influence line, we can solve the rest of the problem. So which part do you want to do first? We've got 3 loads to consider. We've got a live concentrated load of 4 kips, a live uniform load of 300 pounds per foot, and a dead 200 pounds per foot. Yeah, we can do the concentrated live load. So let's do the concentrated live load. Now, live means what?
Moving.
It moves. So we've got a unit load, or we've got a point load of 4 kips. It can be any position it wants in the structure. Where should it be such that it creates the maximum positive moment? Well, you look at your influence line, you find the maximum positive value, which is right there, right above D. So that's where your load will go. So what's the effect of that? It'll be a 4 kip force times this value, which is 10/3 feet, and you get 40/3 kip feet, which is 13.33 kip feet. So that's the moment at D caused by a unit load at this position right here, which happens to be right at D, 15 feet from the left.
What if it's not asking for positive?
Then what would the other possibility be? Negative. So where would the unit load go to create the maximum negative moment? Right here, which would be at 5 feet.
Is that a question to ask for both?
Could. I could just ask you, what's the maximum moment? Right? Positive value is not greater than negative value. It's just direction. So you'd have to do both and tell me which one's the largest magnitude. But you can kind of look at this ahead of time and tell me, is there more positive area or more negative area under the curve? It's more positive area. So that means that when I apply the dead load to the whole structure, I'm going to get a positive answer. And when I position my live load anywhere I want, I'll position it over the positive area. So you can tell right away by just looking, not always, but generally, if whichever area is larger, that's probably going to be the one that's going to dictate. And this is a more positive area, there'll be a larger positive value. All right. So which one do you want to do next? We've got the live load. You want to do the uniform live or uniform dead? Uniform live.
It doesn't really matter, does it?
Nope. I just want you guys to be involved. I want you to make a choice. Or at least think you are. I actually wouldn't do the live load all along anyway. I was leading you that way. Now, it's uniform, so you're going to apply it across a section of the structure, and it's live.
So it's all positive.
So since if I want to create the maximum positive moment, I'm just going to apply it over the positive portion of the influence line. So it's going to start here at C and go to E. So I want just the positive area under the curve. Remember, for uniform load, you're going to multiply the intensity of the load times the area under the curve. But just the positive area. So this particular value is 300 pounds per foot, which is 0.3 kips per foot. And then it's a triangle, so there's my 1/2. And then the base, which is 15 feet, times the height, which is 10/3 feet. So my units will end up giving me kip feet. I have no idea what that's going to be. Somebody's going to have to help me with that.
7.5.
7.5? And that'll be kip feet. So what are we left with? Dead load. So now let's do the uniform dead load. And the easiest way to think about the dead load is just the self-weight of the structure. So structure was that's going to be uniformly applied across the whole structure. So now I'll have to consider both the negative area and the positive area. So the dead load is 0.2 kips per foot. That's the intensity. Again, they're triangular, so 1/2. And now I'll have first this part, which has a base of 10 feet and a height of negative 10/3 feet. And then the positive area, which has a base of the triangle of 15 feet and a height of positive 10/3 feet. So what's that equal to?
1.6 or 1.7.
Anybody else get that?
1.7.
1.7? So then the moment at D would be the sum of all those. This isn't 1.67 by any chance?
Well, 6, 7, 1.7. It's 1.6 for here.
Okay, so that plus that is 20, right? No, it's 15. Plus that would be 22.5, right? Right? No? Yes? This is probably 1.666666. This is 13.33333. Add those two together, you should get 15, right? So it should be 22.5. Is that right? So that's the maximum moment at D. And what does that look like? So if I redraw my structure, so I have a pin connection at A hinge at B, a roller at C, and then all the way out here at E I have another roller. First, the dead load. I'll color code that. We'll do that in green. Well, the dead load has to go over the whole structure. Right? The live load, I'll do that in blue. That only goes what? Over this positive piece. So that'll go from C to E, which would be this part of the curve. And then finally, the live load, I'll do that in orange. Where is it located? At D, which is right about here. So there's my 4 kip load. The live load was 0.3 kips per foot, and the dead load was 0.2 kips per foot. So that's the position of the loading that creates the maximum positive moment. So what would change for the negative moment? Well, the live load would shift where? It would shift to this section of the influence line, which would be from A to C. And where would the concentrated live load go? It would go right over B. But that combination would produce a smaller magnitude moment. But you might need to know both, especially if this beam was made out of concrete. Because remember, these are moving loads. So this is representing, say, an axle of a truck that's doing this all the time. So it would be in this position and create a negative moment at D, and then it would move to this position and create a positive moment at D. So this particular structure, the moment at D is vibrating back and forth between positive and negative as the vehicles move across. So you'd probably have to take care of both of those.
Is the figure required in the test?
What's that?
Is that we have to draw it out?
No, I'm just doing this to kind of help you see what we're doing. Sometimes you get lost in all these calculations. You don't realize that. Remember, this is all we're doing is placing the loads at points that will create the maximum values. And that's, again, all based on the influence line. So if you can't draw the influence line, you're kind of out of luck on this problem. Yeah?
When you're trying to find the forces, how you cut it at B, can you cut it at any point, or does it have to be?
No, I took it apart at B because B didn't have a moment.
Okay. If you do take it apart, say at C, you have to find the moments on each side of that cut?
Yeah.
Okay.
And it would be harder to figure that out. Take advantage of what you have. Okay. Yes. Oh.
It's not really involved with this one, but I know in the homework we had questions where they asked for like the maximum positive shear or maximum negative shear. Mm-hmm. And as far as that goes, how would you use that when you're using the concentrated load, the uniform load, and dead load? How do you add those together? Or,
we could do a problem with shear if you want. I think moment's harder, so I did the moment problem. The shear is actually easier.
well, I mean, we just had one in the homework. Like,
Okay.
that's why I was curious.
Let's stop this.